Good. Okay, today's the second last lecture. In some sense, it's going to finish a sequence of lectures we did about derandomization. So we saw in the last couple of lectures that if there exist functions computable in e or exponential time, which are really hard on average, so like no, say, sub-exponential size circuit can get them correct on barely more than half of the inputs, then BPP can be derandomized to quasi-polynomial time. And today we're going to show a hardness amplification result that we mentioned last time that says, like, well, you actually only need to start with the worst case assumption, that if you have some function that's hard in the worst case for circuits, then you can amplify it into a function that's very hard on average for circuits of a slightly smaller size. And as mentioned last time, we can go from worst case to like very slight hardness, like maybe 1 minus 1 over n or poly n, using these multilinear polynomial encoding tricks. And so then, to get most of the rest of the way, to get the rest of the way from 1 minus something small, like 1 over n, down to half plus something small, we're going to use this tool that I mentioned last time, Yau's XOR lemma. Okay, and so once we have this, we'll pretty much have wrapped up the whole story on derandomization. So let me remind you what Yau's XOR lemma says. It says, let's say you have some function f, and like it's annoying, but I'm going to stick with the bits being called plus or minus 1. So it takes n bits to 1 bit. And it's mildly hard to compute by size S circuits. So I remind you over here what that notation means. It's shorthand for the following. This means that for all circuits of size at most S, the circuit does not do an amazing job of computing f. So the correlation between f and the circuit is bounded by 1 minus delta. And technically that means this. The expected value for x of f of x times c of x is bounded by 1 minus delta. Remember, with this plus or minus notation, like when f and c agree, you're counting 1. And when f of c disagree, you're counting minus 1. So this is basically saying you're counting minus 1 at least a 2 delta fraction of the time. So they disagree with probably at least 2 delta. Okay, so correlation 1 is when they exactly agree. Correlation 0 is like when f gets c right on exactly half the inputs. And what the hardness amplification is saying is that from f, you can fairly easily construct a new function called f, parity k, which is much harder for circuits of slightly smaller size. So the correlation between this new function, f parity k, and any circuit of size at most s prime, this is going to be a small quantity, like very close to 0. And that means that any circuit of size s prime, computes f parity k correctly on like at most a half plus this small fraction of inputs. And right, so you can just briefly to remind you of the parameters. To make this smaller and smaller, you need to take k kind of big compared to delta, which has the effect of making the input length grow from n to n times k. So that's why you don't want to take k like too huge, because it's making your overall hardness, well, it's making input size larger, so sort of the overall hardness less as a function of the input size. And you have this other bottleneck epsilon, which you always pay for down here. So kind of peculiarly, as I mentioned over there, actually the hardness you get for computing this more complicated function is actually for slightly smaller size circuits. That's kind of an inevitable consequence of the way the proof goes, as I'll say in a second. But in particular, it prevents you from taking this like arbitrarily small. Like you can't take epsilon to be 0, because then you get only hardness against circuits of size 0, which is not very good. Well, you can take epsilon to be like, s to the power of 0.001, and that's OK. And finally, what is this hard to compute function? Well, it's quite natural. It's almost like maybe the first thing you would eventually think of. If it's kind of hard for a circuit of a certain size to compute f correctly on a random input, then what this hard function does is takes a bunch of inputs, which they're disjoints. You think of it as a bunch of random inputs, k random inputs. And the function is not a multi-output function. So you have to kind of reduce all the answers to 1 bit. And you kind of do it in like the hopefully hardest way. You take the XOR of all the desired answers. OK? And then the intuition, this intuition, I put a question mark because it's a little bit sketchy. We're going to see a better intuition in a second. But the intuition is that, OK, if you're a circuit of size s or s prime, and you got to compute the parity of f values on k different inputs. It's because it's parity. If you kind of get one of them wrong, that really, even getting one of them wrong, it kind of really messes you up. I'm being vague here, but it seems as though like if you fail to get all k answers right, then you're in big trouble. Like maybe you're not doing better than just the coin flip. Okay, and again, at a vague level, you know, sort of the probability you'll be able to get like one random x's f's value correct on like one random x is like 1 minus delta by assumption. So the probability that you'll get k of them right is maybe 1 minus delta to the k. Okay, that's the intuition. Okay, any questions about this setup? You must have a question or two. Yep.
One thing that I found sketchy about the intuition is that you can get two things wrong and still get the answer right. That's
true.
So even accounting for that, it's difficult, right?
Yeah, so there were several things that were a bit sketchy about this intuition. Maybe a slightly more accurate intuition is like, yeah, I mean, it is about like, you know, do you get an even number of them right or an odd number of them right? And maybe more accurate intuition is like if you're making maybe several errors, you know, if k is a lot bigger than 1 over delta, then you'll probably make like a lot of errors. And then, you know, whether you make an even or odd number of errors might be like close to 50-50 chance. Or another thing to think about is like if you flip a coin, which comes out heads with probability 1 minus delta, k times, and then ask, you know, how close is, you look at like what's the probability you get an even number of heads, like how close is that to a half? It should be something like a half, I mean it is something like a half plus 1 minus delta to the k. So yeah, we'll make this more precise. Other questions? Okay, I should mention, I mean, why, on this peculiar issue, like why do we get hardness for like a smaller size? Well, it's because the proof always goes in the contrapositive. You say like, imagine you have a circuit C, which is good at computing F parity K. And C has some certain size. Good in the sense that like it beats this correlation. Then somehow from it we'll construct another circuit which is just good at computing F on like one input. I mean, that's how the contrapositive will go. And you see that, like, you know, starting from your circuit C that's good at computing F parity K, you'll like maybe add some stuff onto it, and thereby get a circuit F that's good at computing F on one input. And so taking your C and adding some stuff onto it is the reason why the circuit size gets, you know, bigger from here to here. Okay. So in fact, let's talk about this intuition. Let me erase this thing. So let me draw like a meaningless picture to describe the intuition. So like, I want to ask about like the intuition about like, okay, our assumption here is that like F is mildly hard. Like any circuit of size C, like S has correlation at most 1 minus delta for F. So it's kind of, can only compute it correctly on a 1 minus delta fraction of inputs. So like this box somehow represents plus or minus 1 to the n. And like points in this box somehow represent all the strings. And in like scenario 1, like maybe like, I don't know what this means, but like all the hardness is like spread around. Like maybe all the inputs are like kind of equally hard. So like it's just a hard problem. If I pick a random input, it's going to be kind of hard, and like a circuit of a certain size is not going to be likely to be able to compute it. Don't question me exactly what I mean by that. But here's scenario 2, which is, I have more precise things I can say about it. Scenario 2, regarding like why, or like why is F mildly hard like this? It could be like the following. Here is, again, the box for all points, binary strings of length 2 to the, of length n. It could be that there's like some set of inputs here, which I'll denote capital H, which are what Russell and Impagliazzo call the hard core. So the cardinality of H is maybe something like delta times 2 to the n. So it's only a delta fraction of inputs. Let me just, I don't want to get the deltas exactly right, so let's say approximately. And this is, as I said, called the hard core, where for the x's in H, computing f of x is somehow like just hopelessly hard. Hopelessly hard for circuits of, you know, this given size S. And you might think of what I mean by hopelessly hard. any circuit of size S has correlation 0, basically, with f on h. So this is still the level of intuition, but like, the correlation on a random input, not from everywhere, but from just drawn uniformly from h, f of c is basically 0 for all c of size at most s. So like, you remember what this means is like it's barely better than guessing. Like c agrees with f with probability basically a half. And then it could be that furthermore, that like f of x is like trivial to compute when x is not in h. And furthermore, it could be that like recognizing whether or not x is in h is easy. So it could be, potentially, maybe, that f is like this. It has all these three properties. There's some set of inputs, h, the hard core, of size about a delta fraction of the strings, where, I mean, when x is in h, it's just like an incredibly hard function to compute. You may as well, unless the size is 2 to the n, you may as well just guess. But it could be furthermore the case that like when x is not in h, and this is easy to recognize, it's easy to compute what f of x is. And if this were the scenario, then it would still be, then this would still be the case. If I got the deltas right, maybe up to a factor of 2, like 1 minus delta of the time, you have like perfect correlation. A circuit can have perfect correlation, and then the remaining delta of the time, it's got basically 0 correlation. And a couple of things to say about this situation. Turns out that like scenario 2 is like the easiest way for f to be mildly hard, like in the assumption of the Yau-Xor lemma. In the sense that like an f that has all these properties is like the easiest to compute f, which nevertheless has this property. Maybe it's not so easy to see, but like if your goal in life is to compute f, and like I just tell you this fact, then your dream is that like you're in this scenario, because like you can somehow do the best job in that case. And you can see like if you're in this case, now like this intuition, it's a little easier to think about the intuition about computing this. Like now in this case, it's more like, okay, like if all the x's happen to fall outside the h, then you're like, I'm in business, I recognize that, I compute all f values, I get the parity perfect. Whereas if one or more falls into h, you're like, I'm dead, because like I can, if x1 falls into h, you're like, the best I can do is like practically flip a coin to figure out what f of x1 is. And then because it's parity, it's XOR, you're kind of screwed for computing the overall parity. So that's a bit more like where the 1 minus delta to the k comes in.
What should we think of delta to be like order of what? Constant?
It could be anything. In the application we were talking about last time, delta is like 1 over order n. That's the reasonable value to think of it for. Yeah, well, let's say 1 over n is an example. Actually, let me mention one more thing. Here I put delta, and here I put delta over 2. You can actually like work to try to get these like almost the same. But in fact, I'm going to do the opposite in this class. Like maybe I'll eventually prove this with like a 4 here. But like the constant on delta is sort of the least of our worries, because I was saying like typical value is like 1 over order n, so we're not even paying attention to the constant sitting next to delta. Good. And okay, so yeah, that's a bit more. Okay, let me add one more thing. Another thing that turns out, and this is what we'll spend a lot of time talking about today, is that in some sense, scenario 2 actually always holds. And I'll formalize this with a statement in 1 second. But basically, it turns out like just whenever you have the assumption, it's kind of like the converse. Like whenever you have this assumption for any f, it's basically because the situation is like this. Okay, actually, we'll use that in our proof. We'll say, okay, we're assuming that f is mildly hard. Then, because of this bullet point, the situation is basically like this. Okay, and then we'll use the intuition I just mentioned to the more clear intuition I just mentioned to argue that computing f parity k is hard. Really just by looking at okay, what's the probability that a certain number of x's fall or don't fall into H? Okay, so yeah.
So if I was doing scenario 2 for some function and I wanted to come up with some arbitrarily hard function to compute for surface of size S, what's to prevent me from just mapping everything to the n onto H and then saying that mapping composed with f is my function now?
I guess you could, and it would be super hard. I guess one thing that's pleasant about the Yau's XOR lemma, though, is that hardness amplification is simple. It's just XORing together multiple copies of H. It doesn't have to, let's say, compute this projection from all strings into this hardcore. And we relied on that for applications. Remember, so for our hardness, for our derandomization applications, maybe f was some slightly hard function, and we needed f to be computable in, let's say, exponential time, or in 2 to the n time, so that it could be used for a pseudorandom generator. And then we're pleased by the fact that f, parity k, let's say k is n or n squared, that this could also be computed in exponential time, because you just have to compute a few copies of f and parity them together. But if your hardness amplification routine somehow involves mapping a generic input onto this set H, then it might be unclear the computational complexity of finding H or carrying out this mapping. Okay, so the actual instantiation of this claim that scenario 2 always holds is called Impagliazzo's hardcore set theorem, proved by Impagliazzo in 95. Okay, and I will write it down. So suppose it's the same assumption as in Yau that the correlation between f and all the circuits, or any circuit of size S, is at most 1 minus delta. As I mentioned, okay, maybe when I do the proof, it'll be 4 delta or something, but never mind. Then there exists a set H of all strings, and H's size will be at least delta over 2 times 2 to the n, such that the correlation on H between f and circuits of size S prime is at most epsilon, where S prime is, well, as over there, epsilon squared over log 1 over delta times S. Okay, what does this mean? It means the expectation where x is drawn uniformly from H, f of x, c of x, c prime of x, is at most epsilon for all c prime of size at most S prime. Okay. Actually, there's one other super tiny detail which I'll just scratch. This is only true provided S prime is noticeably less than 2 to the n over 2. It stops working if your circuit sizes are like literally close to maximal. But anyway, we're going to be applying them when S prime is even in the most optimistic case, we'll be applying when S prime is like 2 to the 0.0001 n, but more usually when it's like 2 to the n to the epsilon. Plus, the one point where this is going to come up is like the one part that I'm going to kind of skip in the proof. So, never mind. Okay, so is the statement of Impagliazzo's hardcore set theorem clear? Okay, so what we're going to do is prove Yau's XOR lemma, assuming the statement. And then we'll prove Impagliazzo. Okay, so as I mentioned before, it's going to be in like contraposition. So let's say, given f satisfying this hypothesis of both the theorems, suppose we have some C prime. I'll try to use primes for like down here and non-primes for up here. Of size S prime has too good a correlation with F parity K. Call this star. Okay, so yeah, given F satisfying this hypothesis, and given C prime that's good at computing F parity K, we're going to get a contradiction to the hardcore set theorem. So the way we're going to do that is we're going to say, OK, let H be the hard core, which Impagliazzo supposedly promises, and we'll get a contradiction. In particular, we'll get a contradiction to this statement. We'll get a function f which is too good at we get a circuit C which is just too good at computing f. OK, sorry. Thanks. OK. So, contradict Impagliazzo. So maybe this is, yeah. Let H be the hardcore for F. F of size at least delta over 2. Okay, and I guess maybe now we'll contradict this claim. And it follows the intuition that I said before. So we have this hardcore H, and we have this circuit C prime, which is good at computing the parity of a bunch of copies of F. And now let's let R sub L be the set of all k tuples of inputs such that exactly L of the xi's are in H. Okay, and this is for L ranging from 0 to k. Okay, these are all possible, all possible inputs to C prime, are partitioned into these sets RL, depending on how many of the inputs fall into the hard core. And of course, the probability that a random input, to C prime is in R0, that's like the super easy case where like none of the inputs to C prime or F parity K are in the hard core. Well, it's at most 1 minus delta over 2 to the K. So that's the, the set is pretty big. So the probability that they all miss it is at most 1 minus delta over 2 to the K. So in that case, that all the inputs to C prime are outside the hard core, maybe C prime just gets the answer exactly correct. And its conditional correlation with F parity K is perfect 1. But, I mean, its overall correlation is strictly better than 1 minus delta over 2 to the K. It's strictly better than it by an epsilon. So it must be that like it's still kind of decent even ignoring the inputs in R0. Okay, so by star, which is literally right here, there must exist some particular L that's strictly bigger than 0, such that the correlation of C prime with F parity K is beating epsilon on RL. Okay, when you draw a truly random input for C prime, at most this fraction of them fall into R0. Okay, and so it can get that much correlation. But like condition on not falling into R0, the conditional correlation between C prime and F parity K has to be at least epsilon. So by averaging, there has to be one of these sets RL where you're getting at least epsilon. Okay. So I'm going to write something that's, the rest of the proof is actually kind of not that hard, but like it requires some notation. But like imagine like a very simple case where L happens to be 1. Okay? In that case, what it's saying is like if you pick k random inputs of length n, exactly one of which is in H, and the rest of them are outside H, then C prime is kind of decent at computing the parity of F's values on these k inputs. And basically, the way you eventually contradict this, that like F is mildly hard to compute, is like given just a single string, you consider like a random algorithm which randomly chooses k minus 1 strings not in the hardcore, sticks the true input somewhere randomly in this position, now it has k strings, and throws it into C prime. And so now like C prime is experiencing like a random input from like R1, because exactly one of the strings is in H. And C prime is pretty good at computing the parity of the results. And like you can kind of undo the parity of all the k minus 1 strings that you like put in yourself and get like a circuit that's pretty good at computing F on just one input. I'm going to write all this, but that's the outline.
Over here, we're using an assumption that everything outside H is easy to compute.
We don't even need that. We're gonna, because you can like use non-uniformity. So like there's going to be exists ways to like set all the things, all the guys outside H, where C prime is doing a good job, and like you can hard code in the answers for those, even without having to compute them. That'll be like another punchline. Yeah. So okay, we're at this point. There's this magic L. So consider this experiment. I'm going to describe a random experiment similar to what I said before. So step 1, let W1 through WL be uniformly drawn from H randomly and independently. And also let WL plus 1 through WK be uniformly drawn from H bar, the complement of H. So basically pick k random strings where the first L are from H and the last k minus L are from H bar. We're also going to randomly permute these k positions. So let pi be a random permutation of k symbols. And let x1 through xk, these are all n-bit strings, remember, be the reordering of the w's using pi. Okay, so in symbols, xi is defined to be w of pi of I. Okay, but don't get too caught up with the symbols. And now this is a comment. x1 through xk are sort of distributed according to RL. Okay, it's just like k random strings, condition on exactly L of them. Sorry, yeah, exactly L of them being an H. Okay, this is just like a slightly funny way to describe a way to draw from RL. And now, like imagine at the end of this experiment, don't think of any computation or anything yet, just I'm describing a probabilistic Gedanken experiment. Output C prime on this input, x1 through xk, times, or parodied with, if you will, f of x1 through f of xk. Here, I mean, this is just also known as f parity k of the input. And all I was saying is that like when a person does this experiment, I mean, this is sort of measuring the correlation on this particular input of C prime with F parity K. I mean, it's either plus or minus 1, this bit, but like this tells us that the expected value of the final output is greater than, or whatever, greater than or equal to epsilon. I don't know, make this greater. Yeah.
So I had a question about the previous step. How do the correlations add up?
Like,
have a factor of 1 over k somewhere?
like kind of getting to here?
Yeah.
Yeah, so I think I did the calculations correct. We're assuming this. And this is the expectation of this guy times C prime under a totally random input. Now, 1 minus delta, at most 1 minus delta over 2k to the k of the time, that random input is in R0. And in that case, we'll just say like perhaps the conditional correlation, the conditional expectation, is bounded by 1. Okay, so that means the overall correlation can get a contribution of at most 1 minus delta over 2 to the k from that piece.
Right.
Now, the remainder has to come from somewhere. There's one like inequality here that like has to work for us. If it doesn't work for us, it's probably not a big deal. But like, yeah, it's actually working in our favor. So like the remainder of the contribution of the correlation has to be coming from like inputs coming from R1 through Rk. So imagine we just like condition on the input not being in R0. I claim then the conditional correlation is at least epsilon.
Right.
Yeah. And that conditional correlation has some components. It's like some we're conditioning on the input being in R1 union up to Rk. There's some probability it's in R1, some probability it's in R2, some probability it's in R3. And like the weighted average of like the probability it's in R1 times the the conditional correlation with R1 plus the probability it's in R2 times the conditional correlation in R2 plus dot 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 is at least epsilon. So some kind of like weighted average. There's some like weighted probability of being in R1, R2 up to Rk. But like on average over that, the correlation is at least epsilon. So there must exist one component where it's at least epsilon. We don't really need to compute the different probabilities that it's in R1, R2, R3. Although we could, but we don't need to. OK, so in this experiment drawn on this board, the final outcome has expectation at least epsilon. So what do I want to erase here? Guess I'll erase this. Okay, so therefore, there exists fixed. So now I'm going to like fix some of the outcomes in this experiment. I'm going to say for some pieces of this experiment, I'm just going to say there exist fixed outcomes for those pieces where the expectation is greater than epsilon by averaging. So there exist fixed strings. Maybe I'll call them W underline 2 through W underline L in H, and W underline L plus 1, and W underline K in H bar, and a fixed permutation, pi underline in SK, such that the only thing that I haven't fixed actually is W1. So the expectation under W1 drawn from H, of the output, where everything else is fixed, exceeds epsilon. So the overall output is the expectation over all this stuff of this further quantity. So, and if that's bigger than epsilon, there must exist fixed settings for all of this stuff such that the resulting expectation is bigger than epsilon. And this is good because it's like the expectation when I'm just drawing one string randomly from H of something. Okay, so for notational simplicity, without loss of generality, this fixed permutation is the identity permutation. So what does that mean? Let me just write this now clearly. It means the expectation when I draw one string at random from the hard core of C prime, when I plug in the random W1 here, but then I plug in all this like fixed stuff elsewhere, and then times f of, well, the first thing I should write here is f of W1, and then f of the rest of the W's. But let me write that one at the end, and write the rest of them here. This is greater than epsilon. And this, from here out to here, is a circuit which I'll call C double prime of size, well, at most the size of C prime. Oops. Which is at most F's prime, which is doing a good job at computing F with correlation just for one random input in H beating epsilon. Because this circuit only really has one real input, and these are all like literally fixed strings and fixed bits. So we take C prime, plug in all these fixed strings, which exist. That's OK. We're just constructing a circuit, so they exist. And also like modify the output by multiplying by plus or minus 1, depending on all these bits, which exist. And so we get one circuit that just takes one input string, and is like better than epsilon correlation, computing F on that. And this is in contradiction to Impagliazzo's hardcore set theorem. Okay, so because H was supposedly had this property that like any circuit of size at most S prime had correlation at most epsilon with F on the hardcore. So I exactly erased the pain that like had the plan for the proof, but hopefully you remember it. And like this was indeed our final contradiction. Okay, so it's really only important. It eventually didn't really matter what L was as long as there's at least one. We could do this trick.
Why did you use the original assumption of the correlation of
Yeah, let me repeat the plan actually. So we're trying to prove Yau's XOR lemma. So we assume this. And basically then we walk over to Impagliazzo's hardcore set theorem, which has the exact same assumption. And then we pop out H, where it's very hard to compute F on H for this slightly smaller size. And then we want to get contradiction, so we like assume the converse of this, which is that there is some C prime of size S prime, which is good at computing F parity at K. And then we do this reasoning and eventually produce a circuit C double prime of size even smaller than C prime, which is like slightly good at computing F on H. And that's contradiction with this. Yeah, I should have just repeated that line of the proof. That was helpful, I think. OK. Any questions about this? So we're doing everything in like a weird order, but like now we've proved we've proved Yau's XOR lemma about hardness amplification, subject to Impagliazzo's hardcore set theorem, which will now occupy us for the rest of the class. And a reminder, what it tells us is that if you have like a mildly hard function, then the reason is there's some set H whose cardinality is like that of the mildness, where like f is like super impossible to compute on H. And therefore, it's probably actually pretty easy on the rest of, well, anyway, it may be very easy on outside of H. OK, so now how are we going to prove this? It's also bicontrapositive, which is, again, why like why the circuit size S prime like shrinks from going from the hypothesis to the conclusion. And in fact, OK, what does the hypothesis, what does the contrapositive look like? Let's just invert this statement. The contrapositive says, suppose for every set H of size about delta, a fraction of the strings, this fails. So there is a circuit of size S prime or whatever, which is slightly good at computing F just on random strings from H. Repeat. Suppose for every set of like delta fraction of inputs, there's some circuit which is like slightly good at computing F on these inputs. We want to deduce that there's some other circuit which is just like overall good at computing F, in like where the input is drawn totally uniformly at random, but like it's really good. It computes it with probably better than 1 minus delta. If you know anything about like machine learning, this is exactly boosting. It's literally exactly boosting. Like the assumption is that like, kind of like any weird distribution, like even concentrated on like a delta fraction of strings, there's some algorithm which is like weakly good at computing F on this distribution. Then like you start with some hardcore set, get a circuit C which is good at computing a little bit good at computing the function on that set. Then you change the set a little bit and get like another circuit which is good like on the points you're currently getting wrong. And then you change the distribution of the set H again and get like another circuit which is a little bit good at computing F on these things. And you keep doing that and you keep getting a bunch of circuits and you stitch them all together in the end to make like one circuit that's very good at computing F everywhere. So this is exactly like if you have like you can always find like a weak hypothesis for every unknown distribution. Then by boosting, you can like put them together and get like a strong hypothesis for the uniform distribution. OK, so Impagliazzo maybe didn't recognize that at the time, but it was recognized by Clivens and Servideo shortly after. And then they got like, you can get like sort of slightly improve all the parameters here. These are basically close to optimal, but like you can indeed get the optimal parameters by using boosting algorithms from learning theory. Good, so like let's come to, so in fact, in Impagliazzo's paper, like the main part of it was constructing a boosting algorithm. OK, although he didn't say it that way. OK, so proof of Impagliazzo. By contraposition, and our starting point is, so suppose that for all sets H of size at least delta over 2 times 2 to the n, there exists a size S prime circuit C prime, which is like a little bit good on random inputs drawn from H at computing F. OK, this is our supposition. The remainder of the proof. And we got to get a circuit, and it can be a slightly larger circuit. It only has to be of size capital S, which is very good at computing F on the uniform distribution. OK, the first step, it's like a little bit annoying, a little bit technical. We have to make this assumption a little bit stronger, which we can do for free with like a little bit of work. this is about like the correlation of circuits with F when you draw your input like uniformly from a set of size delta times 2 to the n. If you think about a probability distribution which is of the form uniform distribution on a large set, a set of size delta n, this distribution has the property that it doesn't put too much probability mass on any one string. Every string's probability under like this distribution, uniform on H, is at most like 1 over delta times what it would be under the uniform distribution. And we just want to generalize this hypothesis to the same situation where instead of this being like uniform distribution over a set of size delta, fractional size delta, it's like any distribution on all strings, as long as that distribution doesn't put like too much weight, more than 1 minus delta times what the uniform distribution does on any one string. So I'll write that. Say that probability distribution D on n-bit strings is a delta distribution if, okay, on plus or minus 1 to the n, if there's two ways to define it. So one way is to say it's a mixture of distributions of the form uniform on a large set, of the form uniform distribution over H for some H of size at least delta over delta times 2 to the n. Okay, so we've been looking at uniform distributions over large sets of fractional size at least delta. And let's also think about mixtures of such distributions. And any such mixture we'll call a delta distribution. But another, like this is literally equivalent. You can think about it for 1 second. An equivalent way to define these guys is simply that like the probability that D gives to any string x is at most 1 over delta times the probability that the uniform distribution gives to that string, 2 to the minus n, for all x. Actually, one direction is clear. If D is a delta distribution, sorry, if D is a uniform distribution over a set H of cardinality at least delta times 2 to the n, then it certainly satisfies this property. And so if it's a mixture of such distributions, it still satisfies this property. The slightly unclear part is the reverse, that like if D just has this property, no string gets too high a probability, then you actually can realize D as a mixture of like flat distributions that are like exactly uniform on sets of size at least this. Okay, I'm not sure if we'll actually need that direction, but it's true and not hard to prove. I mean, I guess, like this is a convex. The set of guys satisfying this is like a convex set in the space of all, in the 2 to the n dimensional space of all probability distributions. And like the sets that are of the form uniform distribution over set H are like the extreme points of this convex set. Okay. Just let me take that for granted if I need it. By the way, this distinction between these two kinds of distributions, like uniform distribution over a set of size about fractional size about delta versus these kind of smooth distributions, this is exactly this like boring part that I said we were going to like a little bit gloss over. It's genuinely boring, but you kind of have to do it. So here's the boring claim. Let me call this assume this, okay, which we are assuming. That's like the first line of our proof. So under this assumption, we even have a stronger statement, or essentially stronger statement. We have that for all delta distributions D, the same thing. There exists a size S prime circuit C prime with the correlation under D of F and C prime bigger than epsilon over 2 here I'll put. Okay, this means the expected value of f of x times C prime of x when x is drawn from this distribution D. Okay, so if the distribution D is like a particular symbol kind, it's literally just uniform over a set H of cardinality delta times 2 to the n, then we have this, even with epsilon on the right-hand side, by assumption. And we're just trying to like upgrade our hypothesis to even get this. And this is a boring claim. I'm going to give you the proof sketch. But I'm not going to write out, in order to save like 5 minutes, I'm not going to write out all the details. They're in the textbook. Actually, I think it's an exercise in the textbook, though. They're also in Impagliazzo's paper. OK, so the proof sketch. Suppose not, so that this is false, even though the boxed hypothesis is true. So there exists some like hard delta distribution D. So there exists some delta distribution D where this correlation is actually less than epsilon over 2 for all C. And basically, from this hard distribution D, I want to construct like an actual set H of size delta times 2 to the n, where it's also hard to compute F just on this set H. And that will contradict the boxed hypothesis. And the parameters will get like a little bit weaker when I go pass from the this like fuzzy distribution, which is like a mixture of uniform distributions, to like just one particular uniform distribution. OK, so I have this distribution D, and it's like very hard to compute F when a random input is drawn from D. So form a set H randomly by putting each string x into H independently with probability delta times 2 to the n times d of x. And since d is a delta distribution, this number is at most 1. So this formation process makes sense. So basically, I'm trying to turn this like measure into an actual set. And I do it like kind of in the natural way. I like choose elements to be in the set with probability proportional to the measure. And what is the expected cardinality of H? Well, it's the sum of this over all x by linearity of expectation. The sum of d of x over all x is 1, because it's the distribution. So it's delta times 2 to that. OK, so in expectation, H has the right size. OK, now is where I'm going to like start enter the sketch part of the sketch. Let me just say there's a good chance by Chernoff bounds, I just don't want to write all these Chernoff bounds, that like the cardinality of H is at least half its expectation. OK, this is what I'm skipping, but that's why I have delta over 2 here. OK, now I want to claim, towards getting this contradiction, that it's really hard for a size S prime circuit to compute F on this randomly formed H. So what I'm going to do is say, given any fixed circuit C prime, let me look at the correlation of F and C prime on H. Well, but H is random set. So let me look at the expected value of this over the random choice of H. And let me just say, if you just spend 1 minute, which I will not spend, like you have trivial inequalities, to check that indeed this is equal to, this expectation is equal to the correlation of F with C prime under the distribution D. OK, just to save 30 seconds, I didn't write those steps, which is smaller than epsilon over 2 by our assumption towards a contradiction. So again, we have like a random variable whose mean is smaller than epsilon over 2. And again, like by some Chernoffing, there's a good chance over the draw of H that core of H, F with C prime is at most, giving myself some slack, twice this, so epsilon. And then for all C prime of size and most S prime. OK, you have to union bound over the C primes. And that's where this assumption, which I didn't want to talk about very much, comes in. But basically, you just use Chernoff bounds twice in like the natural way. And I assure you that completes the proof. OK, so we like slightly upgraded our assumption that we started with, that for every set that's large enough, there exists a circuit which is not too bad at computing f on that set, to the assumption that like for every distribution which is like smooth enough, the same is true. And that really puts us even more like in the scenario of learning and boosting, if you know about that stuff. Good. So that's the boring part of the proof. And now, actually, this proof is like super nice. Like the good part of the proof is coming up. It's good. We're almost at the like interesting part. OK, so remember, like, OK, just where we are currently, given the boring claim, which we are given because we basically proved it. So this is the boring claim. We want to show that there exists a size S circuit, C, which will somehow be based on C prime. Remember, S is larger by this constant, well, this factor log 1 over delta over epsilon squared, which is quite good at computing f. Correlation under the uniform distribution under all strings of f and c is bigger than 1 minus delta. OK, and as I said, I think I'm actually going to get a 4 in here, so let me write that. OK? Good. So this is the amusing part. Consider the following zero-sum game. OK, I'm going to actually assume you know a little bit about like game theory, just a little bit. If you don't, well, you have to just accept what I'm going to tell you about this. But the following two-player zero-sum game, you know, like paper, rock, scissors, or whatever. So it has two players, who I'll call Cindy, will be the first player. Cindy's role in this game is to pick a circuit of C prime of size at most S prime. So Cindy is the circuit player. And the other player is going to be the hardcore set player. So we'll call the other person Corey. Picks a set of inputs, H, of size at least delta times 2 to the n. OK? And for now, like think of it like paper, rock, scissors, where it's like 1, 2, 3, go. And like Cindy blurts out a circuit, and like Corey blurts out a set. OK? And then, depending what they say, there's payoff. And it's a zero-sum game. So like one person gets points, Cindy, and the other person like loses points. OK? So like the payoff is like plus the correlation under H of C prime and F to Cindy. OK? And like the negative of this to Corey. OK? So like they're both going to blurt out their object. And like Cindy doesn't really know what Corey's going to play, but she's going to try to like output a circuit C prime that's good at computing F anyway. And conversely, Corey is like the negative person. Corey like picks a set where like hopefully it's going to be hard for Cindy's circuit to compute F on that set. But there's some restriction, right? I mean, Cindy's restricted. She can't just like say a circuit of size 2 to the n. Is this bound? Similarly, Corey like cannot just like pick like one input or like two inputs. Like has to give like Cindy kind of a chance by picking like a reasonably large number of inputs. OK, so I can now erase the theorem statement, I think, because all the plan is on the board. This is the assumption we have now. And this is what we're going for. OK? So what I'm going to use about the theory of zero-sum games is that they have a so-called value, which is like, I use the Minimax theorem. So like, in the version of the game I told you at first, right? They both like it's paper, rock, scissors. They blurt out their thing simultaneously, and this is the payoff. Now you could imagine a different version where you force one of the players to go first. And like, in paper, rock, scissors, right, that's rough for one player, right? If you have to go first, then you're going to always lose. But that's only if you're sort of forced to like use a deterministic strategy or a pure strategy. If I make you go first, but I say, you have to go first, but you're allowed to say a probability distribution over moves that you're going to do, then it's actually fine for you. That's the whole point of the theory. It doesn't cost you in that scenario, even though you're forced to go first. You can say a probability distribution on strategies. And even if like the other player now gets to look at your probability distribution and like pick the worst, for you thing to do, in expectation, when like now like a draw occurs from your strategy and it's mated with the other person's play, the expectation of your payoff is like the same as if you had to go simultaneously. And that's true for both players. Right? So obviously in paper, rock, scissors, you should use like the uniform distribution strategy. Like if you have to go first, you say, I will uniformly choose 1/3, 1/3, 1/3 for paper, rock, and scissors. And then the other player, no matter what they do, like they're going to win with probably a half. So like the payoff the value is 0 for both players. And notice also that like if you're the going second player, you may as well use a deterministic strategy. So like the first player definitely has to rely on the fact that they're allowed to say a randomized strategy that they're going to use. But then the second player, they could use a randomized strategy too if they wanted. But actually, if you're overall looking at the expected payoff, then like, the second player can say to themselves like, OK, if I use this randomized strategy, then my expected payoff, where the randomness is over the first player's random strategy and my random strategy, is blah. Well, then there exists like some choice that the second player could make, a deterministic choice, which will also achieve at least blah in expectation. This is this averaging principle we've seen many times. The expected value of a random variable is this much, then there exists an outcome for the random variable, which is at least this much. OK, all of which is to say, this specific game has a value, which is simultaneously the expected payoff when Cindy has to go first and uses her best randomized strategy, and Corey goes second and uses best deterministic strategy. And it's also equal to like the expected payoff when Corey goes first and is allowed to use a randomized strategy and then Cindy goes next and uses a deterministic strategy. This game has a value, just like an expected payoff, nu. And what this means by von Neumann or whoever's Minimax theorem, proof of which is just linear programming duality, I guess. It is equally achieved in expectation by the two following scenarios. Cindy states a distribution on circuits of size, of size that she'll use. And then Corey, looking at the distribution, picks like one fixed h. And it's also achieved in the reverse situation where like Corey states a distribution on h's to use, and Cindy then picks a fixed circuit to use. OK. Now check out the second scenario. Corey states a probability distribution on sets H. And that's really nothing more than a delta distribution. So it certainly is a delta distribution, and actually conversely, any delta distribution can be realized like this. Maybe that's the direction we don't need. I'm not sure. Anyway, Corey's strategy space here, mixed strategy space, is simply Corey gets to pick a delta distribution. And then Cindy picks her favorite circuit to go against that delta distribution. So based on that, like the second scenario, nu is actually equal to the max over all circuits C prime of size at most S prime of, what is the payoff to Cindy here? It's literally the correlation under D of C prime and F. Actually, it's like the minimum over all D. I guess I should have written that. It's the minimum over all D of the maximum over all circuit sizes Cindy could play of the payoff she gets, which is the correlation of her circuit with F under D. But by the boring claim, no matter what D, like Corey states, Cindy has a circuit she can play that'll get her at least epsilon over 2. Okay, so this is at least epsilon over 2 by the boring claim. Okay, so our assumption establishes that this game has value at least epsilon over 2. And now we'll use that fact with this observation. So in other words, in this game, Cindy can get at least epsilon over 2 points on average. But that means she can get it in the scenario where she has to go first, but is allowed to play randomly, and then Corey goes. So it means she has a strategy in the first scenario, which is good, which means there is a distribution on circuits which is good against any fixed set H, which is getting us close to our goal. So therefore, what we've concluded is there exists a distribution C on circuits of size at most S prime, such that for all things Corey can play, so for all H size big enough, delta times 2 to the n, the expected value when you draw a circuit, like when you actually realize Cindy's play from this distribution C, script C, of the correlation under H of C prime and F is at least epsilon over 2. And that's almost what we want. Well, it's pretty good, at least. It's partly what we want. Now, basically what we want to do now, I mean, we're getting towards the end. A little bit like we want to undo the boring claim on Cindy's side. Like she now knows the probability distributions on circuits, which is quite good at, well, it's reasonably good at computing F. And we want to go from a probability distribution on circuits to one actual circuit that's very good at computing F. Well, this is what we'll do. Define the following quantity for each string x. Define the quantity theta of x to be the expectation under Cindy's distribution on circuits of how much she's getting on x. Okay, so for every string, all the 2 to the n strings, just look at how good Cindy's circuit is on that string. Oh, sorry. Look at how good Cindy's distribution on circuits is at computing F on that string. Okay. So roughly, how good is this distribution on circuits at computing F on string x? And one simple claim is that it's actually pretty good on almost all strings. I want to claim that theta of x is at least epsilon over 2, except for, at most, some delta times 2 to the n strings, which we'll call bad strings. Okay. So I want to claim, by virtue of this, is that, okay, maybe there's some strings where theta is terrible. Oh, okay, so the distribution is terrible at computing at them. But there's at most the delta times 2 to the n such bad strings. And in our overall goal of getting a circuit that's good at computing f almost everywhere, we're just going to completely give up at being right at all on these bad strings. But we're going to try to be like super accurate on the non-bad strings. Okay, so why is this claim true? I will ask you.
False, then we can find that many by strings, and this will be our age, and it will contradict that claim for that particular age.
That's right. It just contradicts what's written up here. So like, otherwise, let just h be all the bad strings, which, since we're assuming it's false, is at least this size. And now, like, we not only contradict the star, we contradict it in a strong way. It's like, actually, for every string x in H, this expectation is less than epsilon over 2. And it's stronger than contradicting this, because here we kind of take the average over all strings in H. In fact, like on every string in H, like this distribution of circuits is doing badly. In particular, it's doing it badly on average over H. Okay. Bad strings. Okay, and this contradicts star. Okay. Okay, so good. We're almost done. So as I mentioned, okay, now there's some delta fraction of strings which are bad. We're just in our final goal of constructing a circuit C that's good on almost all strings for computing F. We're just going to totally give up on those strings. But we want to be great at computing F when X is a good string. Okay, so now, say X is a good string. Okay. So for this particular X, when you draw a random circuit from this script C distribution and look at whether or not it correctly computes F on this string, it either does or it doesn't, it's slightly good. I mean, it's slightly bounded away from 0. So like I said, like a slightly better than half chance of computing it correctly. Now, this is like the scenario where like there's a random variable that's like 0 or 1, a binomial random Bernoulli random variable, which is 0 or 1, and its like mean is bigger than a half by like epsilon. Or maybe like you should think about it as like its mean is either a half plus epsilon or it's a half minus epsilon. And you want to make draws from it and guess whether its mean is bigger than a half plus epsilon or smaller than a half minus epsilon. And you can do this by like polling. I mean, just taking a bunch of draws, and you need like something like 1 over epsilon squared draws to like reliably tell the difference. And if you want failure probability delta, you should like add a factor of log 1 over delta to the number of draws you make. So what I'm saying is that if we make, let's say t equals order, bad chalk, log 1 over delta over epsilon squared draws from script C, call them C1 through CT, then accept with probability at most delta the like empirical average, the average j goes from 1 to t of how well Cj is doing at computing F. Well, actually, it'll be within epsilon over 4 of theta. Will be about, I can make epsilon over 4 here by making the constant here big enough, theta of x, and therefore it'll be at least epsilon over 4. Okay, and this is by Chernoff. So you have to know your Chernoff bounds or your sampling bounds to know this fact, but hopefully you've seen that before. Okay. Remember, this is a fixed plus or minus number. And the experiment is like we're drawing a bunch of circuits, computing, plugging x into each of these circuits, and seeing whether it like agrees with this plus or minus 1 number or disagrees. And like on average, it's going to be slightly bigger than 0. So it's like on average, it's agreeing. So in fact, like, when this happens, in fact, whenever this is greater than 0, strictly greater than 0, it means that like among all the T circuits, more than half of them are giving the right answer. That's exactly what it means. And when this happens, it means that this circuit, majority, C1, C2, CT, these guys feeding into X, is computing F correctly. Does that make sense? This is a slightly tricky part of the proof. So we've shown for good X, the probability, and let me call this circuit, let me call this full circuit M. And notice that it's a randomly constructed circuit. You draw T circuit C from this script C, stick a majority gate on top, that's M. So the probability over the random construction of M that M of X equals F of X is very high, at least 1 minus delta. That's what we've shown. And that's pretty good. Now we have a random way to construct a circuit which, on average, the circuit is really likely to compute F correctly on the good strings X. Okay, and therefore, if you think about it for a second, this implies that the expectation under the random choice of F of the fraction of good X's such that M of X equals F of X is at least 1 minus delta. That's a direct consequence of this. Basically by summing this over all x's, or averaging over all x's, and using linear expectation. So as we always do, finally we have the expectation of a random variable is at least something. We're going to say there exists an outcome for that random variable where it's at least this. So therefore, there exists an outcome for M such that M is correct for X, correct about, for F, for at least a 1 minus delta fraction of the good X's. Okay, and now we're really done. So the good X's, fraction of good X's is itself at least 1 minus delta. Okay, so M is correct. I'll fit the rest into here. M is correct on at least a 1 minus 2 delta fraction of all inputs. Okay, which means if you get the numbers right, its correlation, this I put M here, its correlation is at least 1 minus 4 delta with F. And finally, what is the size of M? Well, it's hardly more than the size of the individual circuits. So every circuit down here is size S prime. Okay, and then we take a majority of them, we put in a majority gate that's very small. It's log 1 over delta over epsilon squared times S prime. And that's